Space and time and physical objects are merely the forms of your perceptions, and we cannot, according to evolutionary theory, infer anything about objective reality from them. I look at the moon, I see it when I look. You look at the moon, you see it when you look. We assume that it really does exist even when no one looks. Not according to evolution but natural selection. There is no moon except when you look. And when you look, you create a moon, and when you look away, you don't create a moon. And it doesn't exist. But even more deep than that, space and time exist only as forms of our perception.
Hello guys, welcome to this episode of Little Brains Big Topics. This is your host Mohammed Namati. In this episode we interview Professor Donald Hoffman. Donald Hoffman is a full professor of cognitive sciences at the University of California, Irvine. He is the author of Visual Intelligence, as well as over 100 scholarly articles on various aspects of human perception and cognition. He received the Distinguished Scientific Award of American Psychological Association for early career research into visual perception, the Rustum Roy Award for the Chopra Foundation, and the Troland Research Award for the U.S. National Academy of Sciences. His TED Talk, entitled "Do We See Reality as It Is?" has been viewed over 2.5 million times. In this interview, we discuss his latest book, The Case Against Reality. So, I'll now tell you guys, so first of all, it was a very fascinating interview. I encourage all of you to watch the full 1 hour 40 minutes, I think. So I highly encourage everyone to watch, or if you're listening, listen to the episode till the end. So here is some of the topics we discuss. Evolutionary game theory and the relationship between truth and our brains. We discuss simulation theory, what the skeptics think of Professor Hoffman's theory of truth. We discuss space-time and quantum mechanics, whether mathematics and logics are grounded in truth. Very deep concepts. We discuss whether scientific method can ascertain reality, theory of consciousness, theory of conscious agents, free will, holographic universe, natural selection, presentism versus eternalism. If you don't know what that is, make sure to check out my episode with Professor Dean Buonamano. We discuss his book, Your Brain is a Time Machine. We go in depth. We talk about presentism versus eternalism. We discuss what keeps Professor Hoffman awake at night. And finally, the big question: what's the meaning of life? Yes, you'll have that answered in this episode today. Anyway, hope you guys enjoy the episode. As always, if you have any suggestions for future episodes, you can find us on @big_topics Twitter. That's our Twitter handle. And you can support us on Patreon. Links will be in the description. Also, the links to Professor Hoffman's book will be in the description. Make sure to buy them. Very, very great book. Without further ado, I hope you guys enjoy the episode. Could you tell us what motivated you to write The Case Against Reality?
I've been thinking about writing a book like that for quite a while, partly because I think that there is a good case to be made that evolution has shaped our senses to hide the truth from us. And that's a shocking claim. Most of my colleagues who know evolutionary theory would think that, at least in the case of our perceptions, evolution would shape us to see those truths about objective reality that we need to survive. Not everything. None of my serious colleagues in evolutionary studies would say that evolution would shape us to see all of the truths of objective reality, but most would say that we've been shaped to see some truths of objective reality, in particular the ones that we need to behave adaptively in our niche. And so when I went to study that question, because I'd seen a lot of people just sort of saying that we've been shaped to see those truths that we need to stay alive. But it was just an informal argument. I'd never seen a proof. And you know, evolution by natural selection is a mathematically precise theory. We have evolutionary game theory. We have the replicator equation. You know, we can start to address these kinds of questions with more than just intuitions and hand waves. We can actually say, well, here's what the equations say. So, you know, about 10 years ago, I intrigued a couple of graduate students, Brian Marion and Justin Mark, to work with me. And they wrote simulations using evolutionary game theory, and also Justin Mark did with genetic algorithms. And what they found was that organisms that saw the truth weren't outcompeting organisms of equal complexity that didn't see the truth, that just were tuned to the fitness payoffs. And I'd sort of suspected that would be the case, but you need to see the simulations to confirm that is the case, and then to start to get intuitions about why. And those simulations really did start to give me intuitions about why that I didn't have before. So then I went to a mathematician, Chetan Prakash, and told him what we'd found in the simulations, and told him I thought that there was a theorem or two here that could be very interesting. And so Chetan and I worked together, but of course, you know, he's the mathematician, not me. So when a theorem comes out, it's because of him, not me. And so we've gotten a couple theorems. And so this has profound implications, right? I mean, if I say that one of our best scientific theories, evolution by natural selection, entails that no structure in our perceptions, like the structure of seeing things close versus far, that order relationship of near to medium distance to far, those kind of structural relationships that we see in our perceptions, or the shapes of objects, the colors of objects, none of those properties that we perceive in our, you know, sensory world in any way reflect the structure of the objective world, whatever the objective world might be. That's truly shocking. It's one of the most shocking things I'd ever considered. I mean, there's hardly a statement that you could imagine that's more shocking. Nothing that I perceive in any way reflects the true nature of objective reality, according to evolution by natural selection. So, I mean, that has all sorts of philosophical implications. It has all sorts of personal implications, has implications for religion and science and their relationship. So I realized, you know, it's time. I mean, this shouldn't just be a technical thing. Right now, there's these technical papers. You have to know a lot of math to even be able to read the papers. There's just no way for people to get this important idea. So with some encouraging from John Brockman, who's my agent, I didn't want to do it quite this early. I mean, like any scientist, I want to wait, but at some point he urged me to go ahead and, you know, do it. And so I decided to go with what I've got so far and just present that. So that's sort of why I published that book and why I sort of published it now.
So do you think your ideas might change over time, your current ones?
I hope so.
Oh.
It would be tragic if they don't. I mean, that's sort of the whole point of science, is that our best theories that we have so far, we never say that this is the final theory or this is the truth. That's just not a scientific attitude. It's completely, any kind of dogmatism is like that would be completely unscientific. It's rather, these are the best ideas, the best theories that we have so far, which doesn't mean that they're true, but it means that if you're a scientist, these are the theories that you have to know. You have to study these theories. You have to understand their implications, not because they're the final word, but because they're the best that we've got so far. And so not knowing these theories you just don't qualify as a scientist. If you don't know the theories, you're not doing science. You're doing something, but you're not doing science. If you want to actually move science forward, you have to actually know what the current state-of-the-art theories are in your area of science. And so the reason why I'm studying evolution by natural selection is not because I think it's the final word. Absolutely not. In fact, it may be deeply flawed, but we don't have anything better, right? We don't have anything better, and so it would be irresponsible not to study what we've got. And part of the reason why I study it is it's not easy. When I say that I don't think evolution by natural selection is the final word, and it's not deeply true, I'm not putting it down. It's an incredible theory. It accounts for an incredible amount of empirical data. No other theory comes close. Other attempts to do something instead of natural selection have fallen flat on their face. So when I say evolution by natural selection, isn't the final word, it's not trivial to find something better. And a lot of people have tried and they've failed. And most attempts can be dismissed out of hand as silly. So it's not easy to overthrow a current scientific theory. So it's in that sense that I'm saying that the ideas that I've got from evolution, I hope that they're going to change, but the change will not be trivial. It will require a deep intellectual revolution for us to get the next theory beyond evolution by natural selection. It's not trivial. It's not just anybody can just sort of sit around and scratch their head and go, oh, here's what you need to do. No. It's far more complicated. To even have a shot at getting the next level of theory, you need to spend years understanding why evolution by natural selection is the theory we have right now, all the data and so it's a non-trivial thing to move on. So I am not casually dismissing our current scientific theories. Quite to the contrary. I want to overthrow them. Any good scientist wants to overthrow them. It takes years of study before you're even qualified to begin to think about how you might overthrow them. So no amateur's going to do it. Put it that way.
That's a very good point. And could you give us like a taste of how the mathematical model works, or what its implications are?
Well, yeah, the taste would be like this. It's the theory is called evolutionary game theory, and the word game is very, very helpful here. You can think of our life on Earth and all organisms on Earth as though they're competing in a game. And when you're in a game, right, in many games, what you're doing is you're trying to grab points as fast as you can, shooting stuff, collecting treasures, or whatever it is you might have to do in your game. And if you get enough points in a short enough time, then you may get to go to the next level where it gets harder. But if you don't get enough points, you die, and it's game over. Well, it's sort of like that in evolution. Instead of points, we call them fitness payoffs. So these are fitness payoffs that you get, and instead of you going to the next level of the game in evolution, it's your offspring, your genes go to the next. So it's really, the way to think about it from an evolutionary point of view, is sort of what Dawkins and others have called the selfish gene point of view. But of course, genes don't have any emotions. It's just a nice kind of saying. But it's that, in some sense, it's a competition among genes. The genes are in a big game against each other to see which genes will get into the next generation. And genes use things, from the evolutionary point of view, genes use things like bodies and people with minds as their vehicle to get the gene into the next generation. So if you think about it that way, then it is genes trying to get enough points to survive in the game and pass on to the next generation. From our point of view, as the bodies, the vehicles that they use, we don't get to go to the next generation. The genes do. We're just this transitory thing that a gene used to get to the next level of the game. So from that point of view, we're in some sense secondary. Now, by the way, that kind of attitude, it may be one hint that maybe we want a deeper theory than evolution by natural selection. Maybe we want something in which humans are more special than just vehicles used by genes to get into the next generation. But again, it's not a trivial thing to do, right? Evolutionary theory goes to this gene-centered point of view because the explanatory power of the gene-centered point of view is incredible. And the explanatory power right now in our current theories of a human-centered point of view is almost zero in biological evolutionary terms. So again, I'm not saying someone couldn't come up with a theory in which human significance is central, but no one has figured out a way to do that in a theory that would explain the vast set of biological phenomena that evolution by natural selection. Now, I'll say one thing against evolution by natural selection right now about why we do need to look for a deeper theory, and that is that evolution by natural selection seems to be working pretty well once you have a replicating system like RNA or DNA or something like that. But right now, we have no idea how life booted up. If you take a physicalist point of view, and you have the notion of a big bang where it was just space, time, and energy, no life, no consciousness, and then billions of years of evolution of the physical universe before you get life and then later consciousness. We don't know from within that framework how to go from inanimate and inorganic matter to replicating cells. We don't know how to do that. So and if people are interested in reading a little bit about this in a way that's understandable, there's a wonderful book by Paul Davies called The Demon in the Machine. Paul Davies is a first-rate physicist, and he goes after this very important point that evolution by natural selection is great once you have life and replication. But how you go from an inanimate physical world to the first replicating cell, we don't know how to make that step, and evolution by natural selection will not take you there, at least in our current understanding of it. So there's some deeper, these are hints that there's something deeply missing in our current physicalist and evolutionary theories. Something very, very deeply missing. So I'm all for a revolution in those things, but the revolution will only come from those who have spent years studying these theories and finally get to the point where they understand them and then can take the creative leap to find the next step.
So with the problem of life, so we've done 2 episodes on it, by the way. If anyone listening, they can check out the 2 episodes on origin of life. And the problem seems to be that they don't know how big chemistry is. Do you think you think there's a deeper problem than that? Than just right. We don't know how chemistry turns into self-replicating life.
Right. We don't know how you can. I mean, when it actually gets into all the processes that go on in a cell that are required to maintain the homeostasis of a cell, to maintain the integrity of RNA or DNA, it's unbelievable. There's some kind of information processing now that's going on, and we have to think in terms of information, very sophisticated information processes. And we just don't know how to go from like quantum theory, laws of quantum theory, which can tell us something about, there's quantum chemistry. So we understand from quantum theory some of the basic properties of chemistry, but then the leap from chemistry to replication and the homeostasis that's needed to maintain a replicating system, it's just stunning how complex a cell is. Just an incredibly complex city, and how you get to that complex city with all the workers working together to make the whole thing work, from just basic biochemistry is a leap too far right now. We just don't know how it's done.
And could you tell us about the implications of your models that have about the truth and our brains?
Well, the implications are profound, and that's one reason why I went after it. If evolution by natural selection, if we take that seriously, what it's telling us, what theorems that Chaitan and I have been working on are saying to us is that space-time itself, which is part of our perceptions, right? We perceive depth in space. We perceive sequences in time. These are part of our sensory experiences. None of that's true. None of it is in any way remotely like objective reality. Whatever objective reality is like, it has nothing to do with space and time, if we take evolution and natural selection seriously. Now that's profound. If space and time are doomed, everything inside space and time is doomed. None of this is fundamental. We all believe that the moon is there when no one looks. I'm saying that that's not true. Space and time are not there when no one looks. Space and time are nothing other than the forms of your perceptions. Space and time and physical objects are merely the forms of your perceptions, and we cannot, according to evolutionary theory, infer anything about objective reality from them. I look at the moon, I see it when I look. You look at the moon, you see it when you look. We assume that it really does exist even when no one looks. Not according to evolution of natural selection. There is no moon except when you look. And when you look, you create a moon, and when you look away, you don't create a moon. And it doesn't exist. But even more deep than that, space and time exist only as forms of our perception. So the notion of space and time, so here's the standard theory that most of us believe. Space and time began 13.8 billion years ago at the Big Bang. And there was a period of rapid inflation. And we can see after 380,000 years or so, the cosmic background radiation finally was, emitted. The universe cleared, and we can see the cosmic microwave background radiation. But then space continued to evolve. The huge pre-existing stage of space-time continued to evolve, and that stage was there for probably billions of years before any life ever emerged in this picture. And I'm saying that whole story from the get-go has to be scrapped. Space-time, space and time, and space, and therefore our elaboration of them into space-time cannot be the final reality. They're just forms of our perception. So I turn it around. Instead of saying space-time is the stage, this huge ancient stage, and humans are these little bit players that have just come on in the last few seconds onto the stage, I turn it around. We create the stage. We are the authors of space-time. We're not bit players on space-time. Space-time is our creation, not vice versa. So that's as profound as you can get. The revolution that is required in our perception of what we are in the universe we live in could not be more profound. We're going from space-time being the fundamental reality to space-time merely being a little virtual reality headset that evolution happened to give us. But it's not the final reality. It's just a little visualization tool that lets us helps us play the game. So it's like, so what I'm proposing is that we are like people who've been in a virtual reality game. Like imagine Grand Theft Auto, but a virtual reality version of Grand Theft Auto. And you've just been, suppose someone put on a headset and bodysuit on you the moment you were born, and you've just been in that virtual reality all of your life. That's all you would know, and you would say, "This is it. This is what I see in Grand Theft Auto. That's everything." And I'm saying we have to take the headset off. Space and time is just a headset. Well, now what's outside of it, I don't know. And someone who only knew Grand Theft Auto, if you told them, you know what, there's more to the world than Grand Theft Auto. There's actually, in this metaphor, there's a supercomputer with transistors and voltages and magnetic fields. And that supercomputer is the reality that's just creating this Grand Theft Auto world. Grand Theft Auto world, when you look at the steering wheel in your car, there's no such thing as a real steering wheel. That, when you get the right photons sprayed to your headset, you create a steering wheel. When you look over there, you no longer, the steering wheel literally doesn't exist. There is no steering wheel because you're not creating the steering wheel. There's something in the supercomputer that will spray the right photons to your eyes when you look back, and you will once again create the steering wheel. But there is no steering wheel except in your perceptions. There's certainly no steering wheel in the supercomputer. So this could not be more profound in terms of its implications? To put it very simply, the moon does not exist when no one looks. And in neuroscience, I don't have a brain when no one looks. I don't have any neurons. So strictly speaking, neural activity causes none of my conscious behaviors or none of my behaviors at all. None of my experiences are caused by neural activity. The brain does nothing. Now, in everyday neuroscience, I'm a cognitive neuroscientist, right? So in every day when I'm doing, my work with my colleagues and so forth, of course I will talk about brains and neural systems as though they have causal powers. I'll say that area V4 is responsible for color perception, or the fusiform face area is involved in face perception and things like that. But and it's perfectly harmless for everyday neuroscience. But strictly speaking, if I take evolutionary theory seriously, I literally don't have a brain, and no one has a brain. You only see brains when you look with the right tools, like literally opening up the skull or doing an fMRI or something like that. Then you see, just like the steering wheel in Grand Theft Auto, the steering wheel exists when you look, but when you turn your headset to the side, you're no longer rendering a steering wheel, and that's all there is to the steering wheel. It's what you render when you look. And when you don't look, it literally, explicitly does not exist. So this has profound implications for neuroscience, and then the issue about the relationship between brains and consciousness. Most of my colleagues think that brain activity somehow causes consciousness or is consciousness. And I'm saying from the get-go, no reason to look there. Neurons don't even exist when they're not perceived. They couldn't possibly create consciousness. They're the wrong things. So the implications are profound.
Wow. Okay, there is a lot to unpack here.
You bet.
So, what's the difference between what you are proposing and the simulation theory, basically matrix?
Simulation theory, there's what we have in common, then I'll say what we differ on. What we have in common is saying that in some sense what you see around you is just a simulation, right? This is not the truth. So in that sense, we're saying something very, very similar. You look at the sun, Nick Bostrom might, the people in simulation theory might say, well, that's just a simulation. It's not the truth. But there's two assumptions that they make. They say, well, we're being simulated by some hacker at a lower level, and that hacker might be simulated by another hacker at a lower level, and it could be all these levels, but finally get down to some base level. That's the first hacker that started the whole thing. And you can ask, what's the probability that we're in the base level? And the probability is 0. And so we're probably in a simulation. Well, that base level they assume is a physical world, space and time and some physical hacker. I'm saying that contradicts evolution by natural selection. If you buy evolution by natural selection, then the base level cannot be a space-time physical world. So that's one thing that I'm saying that's different. The second thing that I'm saying that's different is they also have to claim that somehow computer simulations can create consciousness. And right now there's no theory to explain how that could be. The assumption that a computer simulation could create consciousness, interesting idea. There's absolutely no science or scientific theory yet that could ever show that is possible. So, I would love for someone to say, precisely what pattern of computation, or what patterns of computation are necessarily unconscious, and what patterns of computation are necessarily conscious. What pattern of computation must be my experience of the taste of chocolate? If you think that there's some simulation that's going to give rise to consciousness, let's not mess around here. I want to know precisely what computations must be the taste of chocolate and why those computations could not be the taste of vanilla or the sound of a trumpet. No hand waving here. As a scientist, I have absolutely no interest or tolerance for claims that have no scientific backing. None, no interest in the scientific realm. Of course, on a personal level, that's a different story. But when we're doing science, hey, if someone wants to make a scientific claim, then I get very, very hard-nosed. Tell me exactly what computational systems and architectures or processes must be the taste of vanilla, for example, and why. If you can't do that, there's nothing on the table. And right now, the simulation hypothesis has never been able to explain how even one specific conscious experience could be necessarily entailed by any kind of computation. So there's nothing on the table. There's nothing for me to falsify. it doesn't even rise to the dignity of being testable yet. So there's nothing on the table in terms of as a scientist. So I get very, very hard-nosed about that kind of thing. Now, again, if someone in the simulation theory says, yeah, no, we're working on that, we agree that that's a hard problem, we need to work on it, then fine, that's great. If they acknowledge that their hypothesis requires a story there, they don't have it yet, well, yeah, absolutely, then I'm on board. If they deny that there's a problem, then I'm not on board. I mean, I'm too hard-nosed to waste my time with someone who says, oh, we understand that. You don't understand it unless you can tell me where does vanilla come from. Please, just tell me where vanilla comes from in the simulation, the taste of vanilla. If you can't
I agree. Because, yeah, it will be like this simulation will be set in very distant future, even if there is one, because currently we can't make any computers that are capable of having consciousness, let alone having so many people maintaining it. So yeah, it's a bit like saying, oh, we could be all in a dream, right? You can't really falsify it in any way.
Right.
So is there a way we could falsify your theory?
Well, yes.
Is there an experiment you could propose that would show whether, like, if true, then your theory is true; if false, then?
Well, the first things that someone can do is when we've actually published a theorem. So someone could say, look, you got the equations of evolution by natural selection wrong. What you're saying is not a theorem of the theory. So the theorem is out there, it's published, and people, so if someone says that, so at least the claim that we're making that evolution by natural selection entails what I've just said, that can be falsified because we've actually put out a theorem and there's the proof. So someone can look for an error in the proof. So that would be one way to falsify us, right? So this is not a hand wave. It's not I think it might go that way. We have a proof, and if someone can go through and say in line 30 of your proof, you made this mistake.
Has anyone done that?
The theorem's out there and no one's taken it down. That doesn't mean it won't be taken down. It just means, now, of course, the mathematician I work with is pretty sharp. There's not a problem with the theorem.
And has there been any criticism of the general way you might have approached the problem that anyone has told you?
Sure. So we've had some critiques at that level that are quite interesting. So one, they're very, very bright. So Rainer Mausfeld in Germany is very, very smart cognitive scientist, psychologist, brilliant person, and also a personal friend for many years. He critiqued what we've done by saying, look, you're using natural selection. Your theorem is based on natural selection, but there's a lot more to evolution than just natural selection. There's genetic drift. There's all sorts of other things, and many evolutionary theorists think that natural selection is a fairly minor aspect of evolution, right? Evolution has all sorts of things that are involved in it, and the adaptationist point of view in evolution, who knows how much role that plays. So you've perhaps focused in your theorems on a very trivial part of evolutionary theory. When you look at the bigger picture, that's not that important. And I think Rainer Mausfeld's point is well taken. There is a big debate in evolutionary theory about how important natural selection is. There are some who think that it's extremely important, more like adaptationists, like Dennett and Dawkins, for example, who use this. They think that selection pressures are really, really important. But others, like Gould and Lewontin, Stephen Jay Gould and Lewontin, don't think that adaptations are that important in evolution, and so natural selection isn't that important. But my reply to that then, so but you see, as you can see, it's a non-trivial, well-taken point by someone who understands the theory. So hats off, Rainer is a really, really smart guy. But my attitude is this: when people talk about evolution, and they say that because of evolution, we can be confident that we see reality as it is, at least those aspects that we need. The argument that they always give is it makes you more fit to see the truth. Yeah, seeing the truth makes you more fit. Well, that's a natural selection argument. No one says that genetic drift will make you see the truth. They don't say it because it couldn't. How could genetic drift make you see the truth? Linkage, pleiotropy. There's all these other factors in evolutionary theory. No one says linkage will make you see the truth. Pleiotropy will make you see the truth. They say seeing the truth will make you more fit. That's natural selection. So what we did was to say, we don't know how important natural selection is in the overall scheme of evolution. Who knows? But it's the only part of evolutionary theory that has a prayer of shaping our senses to see the truth. And since it's the only one that has a prayer, evolutionary game theory is precisely the tool we need to study that part of evolutionary theory. And so that's what we did. So these are the kind, so you can see the arguments are sophisticated, but then the replies are also have to be sophisticated. And so this is not a trivial game. This is a high stakes game. And the concepts are somewhat complicated.
One might say everything is at stake, literally.
The very nature of space and time and physical reality that we've based all of our science on for the last few centuries. I mean, physics has been, you think about what is physics? Physics for centuries has been the study of what happens in space and time. If space and time are gone, it's not clear what physics is about. That's how deep this is. This is really, really profound stuff. So we're talking about all the cards are on the table. We're all in. This is like all of the big assumptions of science are on the table with this one. And I think we're going to have to let go of space-time. When we let go of space-time, then everything else goes with it. And we're going to have to have a deep conceptual framework to replace it.
And you say we need to let go of a space-time. Do we also need to, well, I guess you mean everything within a space-time as well, biology, chemistry, aerodynamics, aerospace, everything.
That's right.
And
it's all a headset.
Do you also mean quantum mechanics as well, or would you make a distinction?
I think that quantum theory, so Hilbert spaces, unitarity, are just part of the interface.
So just like a space-time, you can throw them away as well.
Special relativity, general relativity, and quantum theory, I think, are all descriptions of the structure of our headset. And when we get, and by the way, I'm not going to throw them away in the following sense. So I'm throwing them away in the sense that I'm saying they're not fundamental. We thought that they were fundamental. They're not. There's got to be a deeper theory that has nothing about space and time, nothing about Hilbert spaces. So there are no Hilbert spaces. There's no Lorentz invariance, nothing like that. And from that deeper, mathematically precise theory, we have to show how space-time, Lorentz invariance, and unitarity, quantum theory, all arise, sort of hand in hand, together from this deeper theory. Now, there's another sense in which I don't throw away our modern theories at all. They're incredibly beautiful. They are deep insights into our headset, right? So, and they're going to constrain whatever deeper theory we come up with. So whatever theory we come up with that is deeper than space-time, we have to not only write down that theory, we have to write down how it projects into space-time. And when it projects into space-time, we have to show how it gives rise to quantum theory, precisely, not a hand wave, the exact equations, the exact scattering. So, I mean, I'm spending my time right now studying scattering amplitudes. 2 gluons at 10 to the minus 17 centimeters smashing into each other, 4 gluons spraying out, 2 quarks smashing. Those scattering amplitudes, I'm studying that stuff because I want to get from a deeper theory outside of space-time of consciousness that I'm working on. It's a mathematical theory of consciousness. I need to be able to show how it projects into space-time, and if I can't predict scattering amplitudes, then no one should pay attention to me, and I shouldn't pay attention to the theory either. So I mean, pay attention in the sense that, you know, if you think it's promising and it's worth working on, but it's not there yet, right? We have to have these kinds of predictions before we can actually say, now here is a scientific theory worth actually saying is worth studying. So right now I'm using the current theory of quantum field theory, scattering amplitudes, also evolution by natural selection. I need to show how the dynamical process on consciousness, why it looks like evolution by natural selection in our space-time headset, or I'm wrong. So all of the current theories, general relativity, quantum field theory, evolutionary theory, all these three pillars, plus all the surrounding science, but those three pillars and the surrounding science, I have to get all of that as a projection, as a special case projection of my deeper theory, or there's no reason to take this deeper theory seriously. So all this work that we've done, I'm not throwing it away. I'm saying, no, this is a beautiful theory of the headset, and it also gives us the tools to test a deeper theory and see if it's worth our attention or not. So that's the game.
Think this is a fact that you'll have a difficult time going about that, I guess, because you're literally finding the theory of everything.
But this one is pretty big because we have to come up with something that gives rise to space-time. So that's pretty big. Plus, it's trying to also capture the structure of consciousness and the dynamics of consciousness. Those are big. So I may not do this before dinner time.
Fair enough. And so here's one point of skepticism I would have personally, and I want to get your thoughts on it. So if space and time, if quantum mechanics, if they're all illusions, then so why do the illusions follow the laws of mathematics? Right. Yeah.
Right. So the argument that I give from evolution that says our perceptions, our sensory perceptions, are almost surely not correct about the world, my argument there does not apply to math and logic. So the evolutionary argument that I give literally does not apply to math and logic. So I haven't, by showing that our senses almost surely don't show us the truth, I have not shown that our math and logic is almost surely screwed up. I haven't shown that at all. In fact, to the opposite, from an evolutionary point of view, a creature that can reason about fitness payoffs properly, 2 bites of an apple give you more payoff than 1 bite of an apple, right? Roughly twice as much. A creature who gets that logic wrong in practice will be in a worse off position evolutionarily than a creature that gets that right. So there are selection pressures. I'll put it this way: the selection pressures for perception are uniformly against any truth, just uniformly against it. But the selection pressures in the case of math and logic are not uniformly against some facility with math and logic, which is different than some. Exactly. I'm not saying that there's any selection pressures to be geniuses in it. Most of us have a hard time balancing our checkbooks, but every once in a while, right? We get a Kurt Gödel, a Hermann Weyl, or John von Neumann. We get these math geniuses that we can all just not jealous as hell of all these people for that kind of talent. That's really hard work for me to do this math. But most of us aren't like that. And this would actually make sense from an evolutionary point of view. At least the selection pressures are not uniformly against some facility with math and logic. And every once in a while, the genes come together and you get a von Neumann coming out. And the rest of us are jealous.
And do you think mathematics and reason and logic, they show us they tell us about reality? Are they grounded in truth, to put it in your words?
Well, 2 aspects to that. One is there is a sense in which reason is not negotiable. which is really interesting. If I want to give you reasons for why we shouldn't trust reason, I've begged the question. In some sense, the starting point, well, I'll put it this way. There are some traditions, like mystical traditions, Rumi, for example, who says the language of God is silence. All else is poor translation. And I absolutely would respect someone who says that and then, being completely consistent, says nothing further. If someone says, look, reason is not the language of God. Silence is the language of God. I can't argue against that. That's perfectly fine as long as they are consistent. But if we're going to talk, and most spiritual traditions write hundreds of pages, they're doing, and they're arguing, right? They're giving reasons. Well, then in some sense, in that case, reason is non-negotiable. You can't use reason to destroy reason without shooting yourself in the foot. So in some sense, one answer to your question is, if I tried to tell you why I thought reason wasn't reasonable, that's impossible, right? I'm caught. Now, but there's another answer to your question, which is, do we discover mathematical truths or do we invent them? Do we discover logical truths or do we invent them? My own inclination is to say that they're there to discover, but I'm not really confident. I must say, on this point, I'm on the fence about whether we construct or discover. I'm leaning on the discover part, but there are these intuitionist mathematical approaches which suggest that there's a consistent way of thinking about math in which, in some sense, it exists, but you're inventing it as you go along, but you're inventing it along certain tracks. So that, for me, that's I'll just have to say I don't know at this point. I'm leaning towards saying we discover mathematical truths, but I have a feeling that there's something to the invention side that I need to understand as well, and I don't understand it yet.
Right. So why do you think the illusion, which is space-time, why is the illusion consistent with mathematics? Because if it's an illusion, then I wouldn't think it has to, why should it have black holes in it? Why should it have gravitational waves? Such very complicated things that we've just been able to comprehend virtually very recently in the human history. Why would those things exist in an illusion?
Right. So from evolutionary theory, you could try to come up with an answer where, in some sense, if it's about fitness payoffs and guiding adaptive behavior, then you want a format that is as compact, simple as possible. And notice that our raw perceptions don't actually give us any hint that the speed of light is universal, right? It doesn't tell us about special relativity, right? It took an Einstein, right? Throughout human history, no one had that idea. Lorentz, of course, had written down the Lorentz, transformations and so forth. But it was the leap of Einstein to say, this is the fundamental feature of our perception. It's not obvious to us using it. And in fact, in some sense, what you see in terms of space is, I'm looking, I see some mountains over there, and then I see the moon rising behind the mountains. Well, the moon looks a little bit further away than the mountains, but it doesn't look 100,000 times further away. It looks a little bit further away. My perceptions are just really off, right? I look at the stars and they look a little bit further than the moon. I don't realize they don't look millions of times or tens or hundreds of millions of times further away than the moon. They just look a little bit. So my perceptions are deeply wrong. So what has science done is taken the predicates of our perceptions, namely space, near and far, and time, and so forth, and started to put them into some kind of order. Like you have an Einstein that comes along, first, a Newton that comes along and says, we can make this look Euclidean. And so Euclidean geometry is good. And then Einstein comes along and goes, no, you need a Minkowski. Minkowski, his teacher, was the one who said Minkowski space, but Einstein's thing ended up being Minkowski space. And so what we have in our current mathematical physics, like special relativity, general relativity, quantum theory, is not something that is directly seen in our everyday perceptions. We don't see Lorentz invariance. We just don't, at least not in a way that we recognize. I mean, once you know Einstein, then you can sort of recognize it all over the place. And the same thing with the quantum theory. You can even recognize, if you're smart enough, I mean, the guys will tell us that the very large structure of space-time is due to quantum fluctuations during the early inflationary period of the universe. So you can see quantum fluctuations writ large on the structure of space if you know what to look for, but most of us wouldn't have known what to look for there. So from an evolutionary point of view, I think the answer that we would give to your question is that there could be selection pressures for our interfaces to be systematic and simple, and therefore describable by simple mathematics. Right? Euclidean mathematics is incredibly simple, right? It's trivial, and once you know Minkowski space, it's not that much harder. I mean, c squared t squared minus x squared minus y squared minus z squared, not that hard, right? And it took a genius to figure out that was the invariant interval. But once you have that, then the rest of the math, not that hard. But that's not our direct experience. And so there could be selection pressures to make the interface have certain simple regularities in it just to keep us alive from an evolutionary story. Now, I may want, if I'm trying to come up with a deeper theory, right, outside of space and time, including outside of evolutionary theory, then I need to take your question at a deeper level. It's a very good question. And I would say that your question is going to have to be I have to have a deep answer to your question for any deeper theory that I've got. Like, if I have this model of consciousness being fundamental, and it's a vast network of interacting conscious agents, then I need to show that the agents will evolve headsets with these kinds of systematic regularities in them. And I can show that from dynamical simulations, hopefully from theorems, not just simulations, but graph dynamics is really complicated. And frankly, it's at the front edges of modern mathematics. Much is not known. So I've got, a lot of new math is going to have to be invented for me to even completely understand the network dynamics of conscious agents that I'm working on. But eventually, your question is a really good one. Why do we have these nice systematic, simply describable interfaces? I gave a hand wave answer from evolution by natural selection. My deeper theory, it can't be a hand wave. It's got to be precise.
Eventually, your final theory will convince me. Got
some work to do. That's right.
Fair enough. What do you think of the scientific method? Do you think scientific method is it just the creation, or is it actually telling us truths? Apart from leaving logic, reason, and mathematics aside, do we ascertain truths from the scientific method?
I think that it's a legitimate goal for science and for scientists to try to come to true theories. I think that's a legitimate goal. I think most scientists have that as their goal. I think that we have failed so far. I think that our best theories, evolution by natural selection, general relativity, quantum field theory, are stunningly beautiful, profound theories. They're not deeply true. They are telling us something very, very important. And I think that they're essential guides in our search and constraints on future theories. But I don't think that they're true. In the same sense that I would say that, in the light of Einstein's special relativity, there's a sense in which Newton's theory is not true. There is a sense. But there is another important sense in which Newton's theory stands on its own as a beautiful, locally true theory. It's true in some sense in its own context. But there's this deeper truth, this bigger mountain that's special relativity and general relativity that we can see are more profound insights. But I think that they're not the biggest hill. They're not the final truth. There's something even deeper. And what's interesting is there's an epistemological limitation that all of us have as scientists. If we happen to be so lucky as to come to a true theory, we can't know that we've succeeded. Because even though every experiment that we use to test it, it passes, we don't know that that's just because we're not smart enough to think of the critical experiment that it will fail. And so even if we came to a true theory, we couldn't be sure that we had it. And so a certain humility is forced on us as scientists. So it's really an interesting situation that we find ourselves in. Most of us are motivated by a desire to find true theories. That's what motivates us. We want to understand, what is this? What's really happening here? What makes this thing tick? What am I? What are we? What's the truth here? And on the other hand, we're forced not to be arrogant, because we know, just look at human history, we have been wrong every time. We've been wrong in very interesting ways. Newton is really, really interesting. Special relativity, general relativity, quantum field theory, if they're wrong in really profound and interesting ways, and they're good guideposts there to what we need to do next. So they're not trivially wrong. And so there's an issue of what I mean when I say they're not trivially wrong. If they're wrong, but they're not trivially wrong, what is that relationship between, I can be profoundly and stupidly wrong. Like say, if I think that astrology has nothing to it, right? I think astrology is like 99.999% nonsense. But why do I think that about astrology, which is false, and say, but not about special relativity, which I'm saying is not false, is not true either, that it's going to be shown to be overthrown. There's something different between the two, right? And I don't know how to precisely spell that out, except that in the case of special relativity, the one thing that is true is that it's made thousands of predictions that we've gone and tested, and it has come through with flying colors. And it's easy enough to get lots of astrological predictions, and every day you can find things that are just falsified. It's just so our goal is to get true theories. We'll never know if we get there. And that also makes me wonder, there's a whole way of thinking about this that it may be wrong. If we're thinking about truth as just some statue, this static statue that's out there that we're trying to understand, where is the statue and what does it look like? That may be the wrong notion of truth. Truth may be a dynamical process. And the thing that makes me say that is if we think about Gödel's incompleteness theorem in mathematics, right? So Gödel essentially proved that there is no end to mathematical truths. No matter how many mathematical truths you've discovered, there will be countless more to discover. Even an infinite wisdom could not know them all. So the process goes on, and so there is, again, I mentioned the intuitionist mathematics. There is this sense in mathematics that I really want to study more and understand, that mathematics itself may not be this carved in stone thing that we just discover. There's a process to it that's really quite profound, what we call the real numbers, the intuitionists say, well, they're not real. They're just random numbers. And there's no such thing as a pre-existing real number. That's a useful fiction that allows us to do certain things like calculus, integration and differentiation and so forth. It makes things easy, but it's just a useful fiction. There are no such things as real numbers. There's just random numbers. It's an interesting idea. I can't dismiss it.
So I think we've successfully pissed off mathematicians as well as all the scientists today.
Well, intuitionist mathematics is a big branch of mathematics, and I'm just talking about intuitionism in mathematics.
Fair enough. Yeah, no, these are this is way beyond my. But I'm glad I can comprehend the depth of the concepts we're talking about.
Yeah, it's sort of in a big go big or go home kind of attitude here.
So could you tell us a little bit about? So we've been talking about truth a lot, but could you tell us about your theory about network of consciousness, and how did that occur to you? How did you come across it?
Well, so realizing that space-time and physical objects may not be fundamental is profoundly shocking. And it raises the question, if space-time and physical objects aren't fundamental, what is? Right? Now, how are we going to try to get at a deeper truth? And our current theories of special and general relativity, quantum field theory, and evolution of natural selection are good enough to tell us that space-time is doomed. But they're not good enough to tell us what's behind it. They're not good enough to tell us what the deeper theory is. They're good enough once we propose a deeper theory to say thumbs up or thumbs down, but they're not good enough to give us a clue about what that deeper theory is about. So that's what makes science fun. We actually have to do a creative leap here. And so that's tremendously fun. But of course the thing about creative leaps is the chance that you get it right is vanishingly small, right? So you go into this knowing that the chance that you're going to get it right is vanishingly small. And if you look back at human history, you see that we're systematically wrong. So in that backdrop, you go ahead and try. And so for me, the intuitions were that we have conscious experiences, taste of chocolate, smell of vanilla, the sound of a trumpet, a headache. Now, I could be wrong. Maybe if those could all be an illusion. If I'm wrong about that, and evolutionary theory tells me I'm wrong about space-time, then literally I'm lost. I'm not right about anything. I have no idea what is a foundational point to begin with, to even start to get at a deeper theory. So for better or for worse, my attitude was, let me take conscious experiences as fundamental. And that means I'm not taking them as the result of brain processes. I'm saying they're fundamental in the same way that a physicalist would say space-time is fundamental. Right? It is the starting point. It's not something deeper. Space-time is the starting point. I'm saying, and once you think about what I'm saying, it's truly shocking. Experiences are the starting point for the scientific theory. That's pretty shocking. Experiences plus, I don't want the experiences to be inert. There's got to be presumably some dynamics here. So experiences need to have a dynamics. Somehow they need to influence the dynamics. So experiences need to inform choices, which are the only kind of dynamics that we could have in this non-physical kind of universe. Is sort of more experiencers influencing other experiencers. There may not be a self. There may not be any self-awareness. I'm not talking about anything like that yet. I'm just talking about raw experiences and choices being made based on those raw experiences. So as a scientist, I have to have certain assumptions. So every scientific theory makes assumptions, right? There is no theory of everything in science. There just isn't. There, if you're in, for example, general relativity, you assume that there's space and time, or space-time. If you don't grant Einstein space-time, he can't get off the ground. But if you grant him space-time, he can write down a beautiful equation. It predicts black holes, cosmology. But there's a miracle, and that is the existence of space-time. That's the miracle. And the miracle gets put in your face when we look at the Big Bang and explanations stop. You have a singularity there, and we just have no idea what's going on. So every theory has its basic assumptions, which are the miracles at the start of the theory. And what you try to do as a scientist is to get the fewest miracles, the fewest assumptions that you can, and then build everything from that. So what I wanted to do, what I call this a theory of conscious agents, I wanted to make the absolute minimal assumptions about the nature of consciousness that I could make. Right? So there's lots of things to say about consciousness. There's learning, memory, problem solving, intelligence, the notion of a self, feelings of guilt, worry about death. There's tons of things, embodiment of consciousness, all this stuff. But if I start with all those things as assumptions, that's a mess. I want to explain those things. I don't want to start with them. So what's the minimal set of assumptions that I could get away with? And it was, there are experiences, and they inform choices. And mathematically, I'll just say what the mathematical statement of it is. The set of experiences that an agent can have is just a measurable structure, probability space, so to speak. And the choices based on those experiences are Markovian kernels, that for each experience gives the probabilities for the kinds of influences you might have on other agents and their experiences. So you have probability spaces and Markovian kernels. That's the math. It's very, very straightforward mathematics in this. And so the network dynamics is really, the links are by Markovian kernels. The nodes are agents with their experiences. And so it's a very, very simple kind of mathematical structure. It's very similar to Turing when he was trying to get a theory of computation, right? There's an infinite variety of computations. You can be, traveling salesman problem, computing pi. There's tons of things that, routing packets through networks, and there's all sorts of things that you could have algorithms for. Turing, trying to get a theory of computation, came up with this trivial formalism, a Turing machine, a finite set of states, a finite set of symbols, a start state, a halt state, and some transition rules. A trivial thing that can only read one symbol on a tape, move left and right, change state, and write one symbol can do. A trivial thing, his assumptions were trivial, but you get all of computation. That's the spirit in which I'm doing this. A trivial thing. A conscious agent only there's no notion of self, no notion of intelligence, memory, learning, problem solving, no meta-awareness. There's just raw experiences, which is measurable space, and choices, which is a Markovian kernel. It's trivial to prove that formalism is computationally universal. Anything that can be done by a universal Turing machine, I can do with networks of conscious agents. So I know that my social networks of these conscious agents are computationally universal. That means that anything that we do in cognitive neuroscience and neural network theories of intelligence, deep learning and so forth, any deep learning algorithm can be implemented in a network of conscious agents. It's a trivial theorem. So I know that I've got the tools in this most simple formalism. I have the tools to build up all these interesting cognitive architectures, and even eventually to build a theory of self out of it. So that's why I'm taking this approach. The motivation is the simplest assumptions possible based on consciousness, because if I'm wrong about consciousness, then I have no idea what I'm right about. And then the proof that the foundation that I've written down is computationally universal. That means I can build up all the rest of the apparatus that I didn't assume. So that's why I have, it doesn't mean I'm right, but at least I'm not wrong from the get-go, right? If someone could prove that my networks of conscious agents were not computationally universal, that would be it. That would be, it would mean I couldn't do it. If someone could prove that there are no such thing as conscious experiences, I'm done, right? Because that's my starting point. But if someone says there's no such thing as a self, I'm good with that, because I'm not assuming a self. But if someone says the self is just an illusion, I have a chance to build a network dynamics that shows how the illusion of a self is computed or created. So that's why. Now, the thing to test this theory, as I said, I have to show how it projects into space-time, where I can make predictions that are testable. And I'll just say at top level how I'm doing that. And this is where I'm spending all of my time right now. My idea is that if we look at not just the detailed behavior of this network of conscious agents, like think about it as like the Twitterverse, right? There's tens of millions of Twitter users, billions of tweets, lots of stuff trending. There's no way that a Twitter user could possibly read all the tweets. There's billions of them. Or interact with all the Twitter. There's tens of millions of them. There's just no way you could do it. So what do you do if you want to understand what's happening in the Twitterverse? If you really wanted to have a good grasp of what's going on where, what's trending in Iran versus what's trending in the United States, what's happening in New York versus what's happening in London, you want a visualization tool that somehow takes in the billions of tweets, millions of users, crunches the data, comes up with eye candy that you can understand. Colorful things, doing simple stuff that you go, oh, what's trending in New York is this, but that's very different from what's happening in Johannesburg, South Africa, where they're really. So you want to create a visualization tool. That's what space-time is. It's a visualization tool. The reality is this vast network of conscious agents, space-time and physical objects like the moon, is just a visualization tool that we use to grok, to understand this network of conscious agents. So I want to show how that visualization tool is created. That's how I'm going to show what physics is. Physics is just a description of this visualization tool. The idea is this. The tool, you can't look at every single tweet all the time, but you can look at what's trending. That's long-term behavior. And you can talk about trends. That's the big idea. You can't look at every single person in New York, but you can say on average, what are they thinking about? What are they worried about in New York? So you're looking at what I'll call this the asymptotic behavior, the long-term behavior. But in dynamics of conscious agents on a graph, so I have a dynamics on graphs, you can look at the long-term behavior of that. And so the asymptotic behavior has nice, clean mathematical descriptions. And I want to show that the mathematical description, the asymptotic behavior of conscious agent dynamics, maps precisely, this is my goal, maps precisely onto certain structures that physicists are finding behind space-time. See, the physicists haven't been sitting on their thumbs going, oh, space-time is doomed, what do we do, what do we do? They've been hunting for the last 15 years and longer for structures deeper than space-time that don't have any quantum theory, that don't have Lorentz invariance, they don't have unitarity, none of that. They're just deeper mathematical structures that give rise to space-time and quantum theory. And they found them. There's things called the amplituhedron, cosmological polytopes, associahedron, and so forth. And what I want to do is to show that the amplituhedron, how it arises as essentially an asymptotic description of the behavior of conscious agents. If I can do that, then I have the path all the way. I have the conscious agent dynamics, its asymptotics gives rise to the amplituhedron, and then the physicists have shown me how to go from the amplituhedron into the scattering amplitudes that you can measure at the Large Hadron Collider. So I'd have a way to go all the way from the step-by-step dynamics of consciousness through its asymptotics, through the amplituhedron, to scattering events at the Large Hadron Collider. And so that's what I'm working on, is that whole path. So there's a lot of math to be done there, but that's sort of where I'm trying to go. If I can actually show precise conscious agent dynamics that corresponds to 2 gluons smashing into each other and 4 gluons going scattering out, and this is exactly what it means in terms of conscious agent dynamics, now I'm onto something, especially if I can make new predictions that you can't do within a physicalist framework, then I'm really onto something. So that's what I'm after.
And I think it would be fair to give you like a Nobel Prize in every field because you will have done everything. But
Well, I'm talking a big story. Let's see what delivers.
and you also think free will is fundamental, is that right?
Yeah, but and I should say how I think about that. So in these Markovian kernels, there are probabilities, right? Given that I tasted vanilla, there's a probability of taking this first action or the second, or probability of taking this other action and so forth. So there's going to be probabilities. Then if I tasted chocolate, then there's these other probabilities for what I'm going to do. So the question is, how do we understand probability? That's the big question. Now, if you're a physicalist, and you suppose that consciousness is not fundamental, agents are not fundamental, it's just a machine. Maybe, but it's a probabilistic machine. So what do we mean by probabilities in that kind of machine? A probability is where explanation stops, right? When you say that, if you're a physicalist and you have a probability, you're saying something, that this is a source into my universe, something new, unpredictable except by probabilities. Something new is coming into my universe. There is a source of novelty, of creation. Probabilities are points of creation coming into your universe. That's the way to think of them. We brush this over and say it's random chance. Think more deeply. When you have a probability in your theory, that is actually a source of creation, ongoing creation in your theory. If it's not an epistemic probability. If you're saying that this is not just a probability because I don't know enough, right? Right in quantum theory, for example, the way the probabilities in quantum theory are interpreted is typically, like, except for some like Bohm and so forth, but the standard interpretation of those probabilities is that this is a fundamental act of novelty in the world. That's what the probability is. When I measure the position of the electron and I have to write down probabilities, it's because there's something new that comes into the universe in the process of measuring that electron. That's brand new creation. Bohm, so theories like Bohm with hidden variables are trying to get rid of that, right? They're trying to say, no, it was only the probabilities were epistemic. It's just you didn't know enough. Einstein wanted that point of view. He wanted to get rid of the probabilities and just say they're only epistemic probabilities. God doesn't play dice fundamentally. It's only God is playing by strict deterministic rules. It looks like dice because we don't know enough, and so it's just our lack of knowledge. But if you take the probabilities as fundamental, they're not just epistemic, and you're a physicalist, then you're saying this is a spout into the universe where new creation is happening. Now, now I say all that just now to get to my area. I'm talking about consciousness being fundamental, and I have the notion of agency possible. How shall I interpret probabilities that are not merely epistemic probabilities? These are like fundamental probabilities. Well, if I say that it's just objective chance, some kind of impersonal source of novelty, then I would be a dualist. I would be saying there's this consciousness stuff, but there's also this unconscious source of novelty, an impersonal kind of probabilistic chance that's leading new stuff. I don't want to be a dualist, so I find myself thinking these probabilities is, if I taste vanilla, the probability that I'm going to take a certain action, how do I interpret that probability? That is describing a free will choice. Now, not unlimited free will. I'm not claiming complete and total freedom, but I'm also saying there's not total determinism, that there is some genuine measure of free choice, some autonomy. Each agent in this network has some autonomy, but of course they're also influenced by the other agents. So there's this modified, so a limited free will. So not genuine, not total free will, but a limited free will, some modest autonomy, and then also some impact by the influences of other agents.
And is there causality in that network?
Right. The only cause would be the free choices. So,
oh, wow.
Right. So there would be the experiences in some sense, influence the choices. So there's some notion of causality there that the experiences, I like to use the word inform, because I don't want to say that they cause the choice. It's rather that they inform the choice, and that there's this. So the agent has experiences and has some freedom to choose, but it's not independent of the experiences. So it's sort of subtle, right? The how we think about it is really interesting. The math is straightforward. I have a measurable space and a Markovian kernel. Couldn't be simpler. So the math describing what I'm talking about is straightforward. How I want to think about it is interesting, and does that lead me to any other new formalism later on? This thinking about influence versus determining and limited free choice. So you can see what I'm doing now is I'm not doing math. I'm thinking about what the math is saying to me, and that's actually the direction that it came down. Is that I wrote down the math first, and then other people pointed out to me, Don, you're saying that there's free will here, and by the way, you're also saying since the free will is a Markovian kernel, then there's got these probabilities, and I'm saying the only thing that's conscious experiences are the measurable space of conscious experiences. I'm saying that there's an aspect of free will that's unconscious, necessarily unconscious, that we can't be totally conscious of our free choices. The and I didn't when someone's pointed that out to me, I said, that's not true. I didn't say that. I didn't mean that. And they said, well, look at your math. And I went back and I go, the math came and slapped me in the face. And I looked at it and go, holy smoke, it's saying, yeah, what I didn't intend to, but what I wrote down is saying there's a deep aspect of free choice that's necessarily unconscious. So I had to sit on that for a few days. And am I good with that? And the math sort of made me come around and go, well, I better be good with it because I can't think of a better way to write this thing down. So the math comes back and tutors you. So that's one reason why we do math, right? In the case of Einstein, right, his general theory of relativity, it's very famous that like in 1907 or so, he had the idea, he called it the happiest idea of his life, that if I was in an elevator that's free falling, I would be weightless. And from that idea, that's the key idea to launch the whole theory of general relativity. That's the big idea. But it took him, I don't know, eight years or something like that of hard work, sleepless nights, emotional trauma, wrestling with mathematics, learning new mathematics, sweating it out before he could take that idea and turn it into math. And it was so in 1915 he finally gets the math, and it nearly killed him. It was really hard. So he gets the math. He's turned the elevator falling and weightlessness into an equation. Within a year, the equation came back and slapped him in the face. Someone showed that there were singularities that we now see as black holes. And basically, for decades, Einstein did not like black holes. His theory was smarter than him. I mean, and if theory is smarter than Einstein, theories are really smart. So that's why we do these mathematical theories, and that's why I'm very insistent on myself that I take all of my intuitions about consciousness and write them in mathematics. If I don't write them in mathematics, I don't know what I'm talking about. If you don't write it in mathematics, you don't get the wonderful tutoring that the mathematics does back to you. You write down the math comes back and it becomes your teacher. And if you don't do things in mathematics, you lose the chance to find out what you really thought. So the mathematics came back and told me, Don, if that's what you really think when you write down your mathematics about conscious agents, that means you think that there's an aspect of free will that is necessarily unconscious. I don't think that. Yes, you do. Go look again. And I had to go back and look again. And so that's the power of taking our intuitions, turning them into math, because the math then it gives you training wheels for your head so that you can take the next step. We're not smart enough, at least I'm not smart enough, and if Einstein's not smart enough to figure out black holes, then we're in good company, right? And if Einstein's got trouble, then the rest of us are deeply in trouble.
I mean, that's fascinating because I would have imagined people, if someone came with a theory that showed any free will, I would have assumed, oh, they must have smuggled it in somewhere in their premise initially. But no, in your case, it seems like it just came out at the end.
I just wasn't smart enough to realize what I was writing down had all these implications, but I think I'm in good company. Most of
Wow.
us, when we write down our mathematics, we aren't smart enough to realize all the implications. That's why we write down the equations, and then we spend years studying the equations, and they tutor us.
So this thought just occurred to me right now. So if you used natural selection to derive your theorem, and then your theorem says nothing is true, wouldn't that include natural selection itself? And are we not stuck in a paradox then?
Right. So absolutely. So here, but this is the neat thing. So evolution by natural selection entails that space-time and objects are not fundamental. And that means that DNA is not fundamental, which is an essential part of our current understanding of evolution by natural selection. So what do we do as scientists? What we have to do is come up with a deeper theory. I'm proposing this network of conscious agents and its dynamics.
So natural selection could be true
in the interface.
Oh,
it's true of the interface, but not true deeply.
Okay.
It's a true description in the interface. See, that's how we do it in science, right? So when quantum theory and special relativity or gravity in quantum theory tell us that space-time is doomed, and that therefore those theories themselves are doomed because they're theories of space-time, right? Right. Quantum theory assumes space-time, and it's saying that space-time is doomed. So it's in some sense shooting itself in the foot, right? It's saying, it's taking down space-time, but quantum theory is on that ship. It's based on that ship, and so of course general relativity is a theory of space-time. So when they both tell you that space-time can't be fundamental, they're scuttling the very ship that they're on. But what we don't say that they're deeply wrong. We say that there's a deeper framework. And we're looking for a deeper framework, and then we have to show why, as a special case, we get something that looks like space-time as a projection of this deeper theory. And then within that theory, within that deeper framework, we want to see why it looks like evolution by natural selection, it looks like general relativity and quantum field theory in our interface. So science, so far, 99% of science has only been a study of our interface, not objective reality. We have never really, in science, stepped out of the interface to study truth, but we're starting to. We have the tools to do it, and then everything that we studied will not be deeply true. It will, like evolution by natural selection, it'll just be true as a projection in our interface. So it's the right projection in our interface of a deeper dynamics. Evolutionary dynamics is just a tiny projection of a deeper dynamics of consciousness. Same thing with physical dynamics. Physical dynamics is just a headset projection of the deeper dynamics of consciousness. That's the hope. Wow.
Very interesting. I just a few more questions, and then I think that. So do you know Dean Buonamano?
I know of him. Yes, we haven't met, but yes.
Right. So I had him in one of the previous episodes, and we were talking about the distinction between eternalism and presentism. I was wondering if you were familiar about how. So in the block universe,
right.
From general relativity, they tell you, past, present, future already exist. There is there is no arrow to time. There is no present. Present is an illusion.
Right.
But the way we experience consciousness is just we are trapped eternally in the present. I was wondering if you had any thoughts on that.
Right. So the block universe point of view, which Einstein seemed to hold to, says that in some sense the entire space-time loaf, or the whole block, exists, right? There's the notion of present, which seems so psychologically compelling, has no special notion in special relativity or general relativity. And my attitude toward that is that the whole discussion there is assuming a physicalist framework, which is what I'm rejecting. I'm rejecting that from the get-go. So the idea would then be that space and time themselves, those predicates, the predicates of space and time, are the wrong predicates to describe objective reality. They're only headset predicates. And what's true psychologically is that the present is really important. Now, here's one objection that someone could give to what I'm saying, and that is to say, your work here is only talking about observation, not measurement, right? So people observe, but scientists measure, not just observe, they measure things. And in the case of special relativity, right, I might, there's the standard thing in special relativity of, you have a train and a boxcar and two people at opposite ends of a boxcar and a light bulb right in the middle, and the light bulb flashes and the photons go, and if you're on the train, in the frame of reference of the train, the two guys in the boxcar see the light simultaneously. It looks like it's simultaneous for them, right? But if I'm on a platform and the train is going by, then the train is going this way, the guy on the side that's in the direction of motion, from my point of view on the platform, he will get the light later than the guy on the other side, right, on the left side. And if we take all of our observations and we use special relativity and all the equations and so forth, we can actually measure things. And the idea is that if we measure things and we say, that guy on the train could get it later than the guy over here, so it's not simultaneous. It's only simultaneous for me. But from my point of view, the guy on the train is not simultaneous with the other guy in getting the light. But on the train, they think it's simultaneous. Someone might say, well, with that kind of measurement, using the computations that we get from special relativity, we've gone beyond observation and we've gotten to reality, right? And the reality is a space-time loaf, that there's this space-time loaf in which the notion of simultaneity is gone. And I'm saying, no, we haven't gotten to reality, any more than suppose you have a bunch of guys playing Grand Theft Auto, on the virtual reality version. And what you see in Grand Theft Auto is, I can see down the street, but the mountain down there doesn't look much further than the moon in the simulation and so forth. But you start working with all the other guys that are playing, and you start making measurements to each other, and you find out that it's a Newtonian world. That you drive along these roads, and in the Pythagorean theorem, in the Euclidean version of it, holds in your world. So you've actually made a measurement. You go, aha. So I've gotten beyond just observation in Grand Theft Auto. I've got to reality. Well, not absolute reality, just the structure of the game. You're still in the game. Special relativity and the block structure, Einstein's space-time block, is just the structure of the game. It's not the deep objective reality.
What are your thoughts on holographic universe?
Well, the holographic principle in physics is quite profound, right? So Juan Maldacena, back in the late 90s, for anti-de Sitter space, discovered that string theory with gravity in the inside of the space, what they call the bulk, is exactly the same as a standard vanilla quantum field theory on the boundary with one dimension less. So they're the same thing. So in anti-de Sitter space, a theory without gravity, with no gravity at all on the boundary, is identical to a theory with gravity in the bulk with dimension +1. But that's only for space, right? Time on the boundary and time in the bulk are the same time. So that's not a complete holography. You're not getting the holography of space-time. You're only getting space emerging, not space-time. So there's no deeper holography yet of getting space-time, not just space. And the anti-de Sitter space stuff, of course, isn't our world. I mean, we're in a de Sitter space. And but the holographic principle, I think, is really quite interesting, and it may be pointing to the kind of thing I'm saying, which is space-time is just a headset. It's just a projection of something deeper.
Very interesting. I also know that you meditate 3 hours a day. Has meditation given you any insights into the nature of consciousness?
Well, it certainly has made me have to take it quite seriously. I've not had the kind of profound, a lot of people will have like these profound kinds of earth-shaking kinds of things in meditation, much like, you know, a profound drug experience. That's not been that way for me. It's been a more systematic, gradual transformation. The transformation that I find happening in meditation, and I'm sure it's different for everybody. It's different paths. We're each unique. But for me, I think it's much like what I think was going on with metamorphosis. A caterpillar turning into a butterfly inside a chrysalis, right? That sounds wonderful, right? You go, hey, caterpillar, how would you like to be a butterfly? Sounds good to me. Let's do this thing. Well, but it turns out, for that to happen, the caterpillar has to let go of everything it knows, right? All it knows is crawling along on green leaves and eating them. And when you actually look at what happens inside the chrysalis, it's not all love inside there. The immune system, the immune cells of the caterpillar seek and destroy. They kill the cells that are responsible for the transformation into a butterfly. It's an immune response. This transformation is viewed by the immune cells of the caterpillar as some kind of foreign infection, and it has to kill it. And it continues to try to kill the cells that are going to transform it into a butterfly until it gets overwhelmed. And then almost the entire structure, not all, but much of the structure of the caterpillar gets liquefied. Now it can't be fun to have your body liquefy. Everything, I mean, that sounds immensely painful. But then eventually the goop gets reassembled into a butterfly. And eventually it takes off in realms that the caterpillar could never even dream about. That's what I think meditation does. It's a complete restructuring of the personality. And in the moment, most of my reaction is that of the caterpillar, like, what the is going on? It's just like painful. But after long periods of it, you begin to realize, wait, there is some deep, complete restructuring of the personality that's going on here that I, as a caterpillar, still am not really able to understand. I just have to let the process happen and see what goes out and sort of trust the process. But what I find is that my innate response is to fight it all the way. And what I have to do is choose not to fight and to let the transformation go. So for me, it's not like, it's a magic carpet to bliss and I go in there and all is well. It's rather, I'm going into the chrysalis and I'm liquefying and it hurts like hell and I have no idea where it's going to end up, but somehow I trust the process and I'll let it happen. So there's again that kind of, it's humbling, right? I don't know. There's no room for arrogance, and science has no room for arrogance either, which is really quite interesting. What I learned from science and from meditation is, of course, learn as much as you can, try to understand as much as you can, but always admit and understand that essentially you know nothing.
Wow. What question keeps you awake at night?
Well, right now, the question for me, it's a technical question, right? Is how can I map the asymptotic behavior of conscious agents into the amplituhedron or the cosmological polytope? So it's a very technical question that, and I try not to let it keep me up at night, because my guess is it's going to take me, given my my lack of talent, it's probably going to take me 2 or 3 years of hard work to solve that riddle. This is not, there's a lot of technical stuff. So 2 or 3 years of hard work. So I have to learn not to let it keep me up at night, because you can't afford to have a lot of sleep. But but that's the thing that really is on my mind right now. There are, of course, I think you're asking about deeper questions, like what is there life after death, and what's this all about, and so forth. And I do think about that.
In fact, that was my last question. What's the meaning of life? So,
well, my attitude on that is I don't know, but there is one idea, and only one that I found so far, that seems deep enough to be worth at least considering seriously. And that again comes from Gödel's theorem, which, remember, is about the idea that there's no end, in principle, there's no end to the discovery of new mathematical structure. No end. And in a universe in which consciousness is everything, that's what it's about. Consciousness, conscious agents are fundamental. That's what it's about. Then that means in that universe, if that's correct, then mathematics is all and only about the possible varieties of consciousness. And that leads to an idea that I call Gödel's candy store, which is there's an infinite variety of conscious experiences. And Gödel's theorem guarantees that it's endless. There's no end to the exploration of Gödel's candy store of all the varieties of consciousness. And so what is consciousness up to? Why is there a dynamic at all? Well, there's a dynamic because, in principle, there's no end to the exploration of the possible varieties of consciousness. So that's why there's something for consciousness to do, because of Gödel. There's something for consciousness to do, which is enjoy the endless variety of the candies, the varieties of consciousness in Gödel's candy store. So I don't know if that's right, but at least it's not trivially wrong. At least I'm not smart enough to find out where it's trivially wrong. And that's the kind of idea that I would love to see others explore. I mean, maybe that one's not right, but ideas of that ilk, where we have some deep principle that we can say this is the principal reason for what's going on, why there is consciousness, and why consciousness doesn't just sit here and do nothing. Why is consciousness doing something? Well, maybe it's doing something because, in principle, there's endless consciousness to explore.
Endless consciousness to explore. We'll leave it there. Thank you very much for your time.
Thank you very much, Mohammed. It was a great pleasure.